Hi, I am Dhanalakshmi, Assistant Professor, PG Department of Mathematics. Now, see about the topic about complex analysis, probability, and the complex function. Now, you will learn functions of complex variables, limits, continuity, and differentiability, analytic function, and the connected theorems, and some properties of analytic functions, harmonic probability property, or orthogonal probability. In the system of real number, or we can solve all quadratic equations of the form ax square plus bx plus c, a not equal to 0, and the discriminant b square minus 4ac greater than or equal to 0. When the discriminant b square minus 4ac is less than 0, the solution of this quadratic equation do not belong to the system of R. In fact, the simple quadratic equation of the form x square plus 1 equal to 0 does not possess solution in real. This difficulty was overcome by introducing the imaginary part unit I, where I square equal to minus 1. Thus, the set of complex numbers defined as C equal to set of all x plus iy, comma x comma y belongs to R and I equal to root of minus 1. Some basic results. If z equal to x plus iy is a complex number, then the complex number z bar equal to x minus iy is called complex conjugate of z, and z bar is also equal to x square plus y square, that is also called R. Next one, a complex number z is x plus iy is represented by a point p of x comma y in the Cartesian plane with abscissa x and ordinate y. Then x-axis is called real axis and y-axis is called imaginary axis. The point p of x comma y is referred to as a point z. Let OP equal to R and XOP equal to theta, then X equal to R cos theta, Y equal to R sin theta. Every complex number Z can be expressed in the form as given below. Z equal to R into cos theta plus I theta is a polar form, and Z equal to R into e power I theta is an exponential form. Next one, we observe that R equal to root of x square plus y square is the modulus of Z, and it represents the distance of the point from the origin also. Also, theta equal to tan inverse of y by x. The angle theta is called the argument of z. Now, let z naught equal to x naught plus I y naught. Then, modulus of z minus z naught equal to root of x minus x naught whole square plus y minus y naught whole square. Now, z minus z naught may be represented as r into cos theta plus I sin theta, and modulus of z minus z naught equal to capital R. So, the complex equations of the circle C with is x naught comma y naught and radius R. In particular, modulus of z equal to 1 represents a circle with center at the origin and radius equal to 1. Next one, functions of complex variables. Let C be a set of complex numbers of if to each complex number z in C there corresponds a unique complex number w, then w is called complex functions of z defined on C, and we write w equal to f of z. Hence, w has a real part, say u, and imaginary part, say v. Then w has represented as w equal to f of z, that is u of x comma y plus iv of x comma y is a Cartesian form, u of r comma theta plus iv of r comma theta is a polar form. Next one, continuity. A complex valued function f of z is said to be continuous at a point z naught if f of z is defined at z naught and limit z tends to z naught f of z equal to z naught. Next one, derivative of a complex function. The derivative of a complex function f at a point z equal to z naught defined by f dash of z naught is defined as f dash of z naught equal to limit delta t tends to 0 f of z naught plus delta z minus f of z naught divided by delta z, provided this limit exists. Substituting delta equal to z minus z naught, we have f dash of z naught equal to limit delta t tends to 0 f of z minus f of z naught divided by delta z. We should remember that by the definition of limit f of z is defined in a neighborhood of z naught, and z may approach z naught from any directions in the complex planes. The derivative of the complex function at a point is unique if it exists. Next one, Cauchy-Riemann equations. What is Cauchy-Riemann equations? Cauchy-Riemann equations provide a Cartesian criterion for the analyticity of a complex function w equal to f of z, that is also equal to u of x plus y plus iv of x comma y. Next one, what is Cauchy-Riemann equation? Necessary condition for the function to be analytic. If f of z equal to u of x comma y plus iv of x comma y is continuous in some neighborhood of a point z equal to x plus iy and its differentiability at z, then the order of partial differential equation of u of x comma y plus iv of x comma y exists and satisfy the Cauchy-Riemann equation ux equal to vy, uy equal to minus vx at the point z equal to x comma x plus iy. Now the proof of this Cauchy-Riemann equation is, since f of z is differentiable at z, we have let us assume delta z to wholly real and wholly imaginary. First case 1, if delta z is wholly real, then delta y is also equal to 0. So that delta z equal to delta x, the limit on the right side of the equation 1 becomes f dash of z equal to limit delta x tends to 0 u of x plus delta x comma y minus u of x comma y divided by delta x plus I into limit delta t tends to 0 v of x plus delta x comma y minus v of x comma y divided by delta x, that is also equal to ux plus I vx. Next case 2, if delta z is wholly imaginary, then delta x is equal to 0. So that delta z equal to I into delta y. The limit of the right side equation of 1 becomes f dash of z equal to limit delta y tends to 0 u of x plus y comma y plus delta y minus u of x comma y divided by I into delta y plus I into limit delta y tends to 0 v of x comma y plus delta y minus v of x comma y divided by I into delta y, that is also equal to 1 by I into uy plus vy, that is also equal to vy minus I uy. Okay, since f of z is differentiable, the value of the limits obtained from 2 and 3 must be equal, that is ux plus ivx is also equal to vy minus I uy. Comparing the real and imaginary parts, we get ux equal to vy, uy equal to minus vx. These are known as Cauchy-Riemann equations. Satisfaction of this equation is necessary for differentiability and analyticity of the function f of z at a given point. Thus, if a function f of z does not satisfy the Cauchy-Riemann equations at a point, if it is not differentiable and hence not analytic at that point. Now see the example. If w equal to f of z, then dw by dz and determine w is not analytic. Let us consider z as an exponential form, then w equal to log z, that is w equal to u plus iv equal to log of x plus iv equal to 1 by 2 into log of x square plus y square plus I into tan inverse of y by x. Equating real and imaginary part, u equal to 1 by 2 into log of x square plus y square, v equal to tan inverse of y by x. Differentiating u and v with respect to x and y, we get ux equal to x by x square plus y square, vx equal to y by x square plus y square, and uy equal to y by x square plus y square, vy equal to x by x square plus y square. Now from the CR equations, ux equal to vy, uy equal to minus vx. Okay. Thus w equal to log z, the CR equation holds good for x square plus y square not equal to 0. Further, dw by dz equal to dou u by dou x plus I into dou v by dou x, that is also equal to x by x square plus y square minus I by iy by x square plus y square. Thus every point other than the origin, that is x square plus y square not equal to 0, w equal to log z is differentiable and the function log z is analytic everywhere except at the origin. Same thing we see about the next example, w equal to sin z. Here sin z equal to x plus iy, then w equal to sin x cos iy plus cos x sin iy. Now sin x equal to e power I theta minus e power minus I theta divided by 2i, cos x equal to e power ix minus e power minus ix divided by 2. Okay, therefore w equal to u plus iv, that is also equal to sin x cos hy plus I cos x sin hy. Equating real and imaginary parts, we get u equal to sin x cos hy, v equal to cos x sin hy. Here ux equal to find ux uy, vx, vy. The CR equations are also satisfied. Hence, f of z equal to sin z is analytic. Next, consequence of CR equations. If f of z equal to u plus iv is analytic function, then u and v both satisfy the two-dimensional Laplace equation. Dou square phi by dou x square, dou square phi by dou y square equal to 0. This equation also known as del square phi equal to 0. Here del square is the two-dimensional Laplacian. Since f of z is analytic, we have CR equations ux equal to vy, uy equal to minus vx, differentiating 1 with respect to x and 2 with respect to y. Partially, we get dou square u by dou x square equal to dou square v by dou x dou y, and dou square u by dou y square equal to minus dou square v by dou y dou x. But dou square v by dou x dou y equal to dou square v by dou y dou x all is always true, and hence we have dou square u by dou x square equal to minus dou square u by dou y square, or dou square u by dou x square plus dou square u by dou y square equal to 0. This implies u is harmonic. Similarly, differentiating 1 with respect to y and 2 with respect to y, partially we get dou square v by dou x square equal to minus dou square v by dou y square, or dou square u by dou x square plus dou square v by dou y square equal to 0. This implies v is harmonic. If f of z equal to u plus iv is analytic function, then u and v are harmonic functions. Hence, u and v are called harmonic conjugate of each other. Consequence 2. If f of z equal to u plus iv is an analytic function, then the equations u of x comma y equal to c1 and v of x comma y equal to c2 represent orthogonal families of curves. Solution: u of x comma y equal to c1, v of x comma y equal to c2. Differentiating this partially with respect to x, we get dou u by dou x plus dou u by dou y into dy by dx equal to 0, or dy by dx equal to dou u by dou x divided by dou u by dou y, that is equal to m1. Differentiating again partially with respect to x, dou v by dou x plus dou v by dou y into dy by dx equal to 0, that is dy by dx equal to dou v by dou x divided by dou v by dou y equal to m2. The two families are orthogonal to each other, then m1 into m2 equal to minus 1, and using CR equations, m1 into m2 equal to dou u by dou x by dou v by dou x divided by dou u by dou y into dou v by dou y, that is also equal to m minus 1. Hence, the curves intersect orthogonal at every point of intersections. Next one, some important forms of CR equations. If w equal to f of z, that is equal to u plus iv is analytic, then the following results follows. F dash of z equal to dou u by dou x plus I dou v by dou x, that is equal to dou v by dou y minus I dou u by dou y, that is also equal to minus I into dou u by dou y plus I into dou v by dou y, that is also equal to dou minus I into dou u by dou y plus I into dou v by dou y. Next one, modulus of f dash of z square equal to dou u by dou x whole square plus dou v by dou x whole square, and modulus of f dash of z whole square also equal to dou v by dou x whole square plus dou u by dou y whole square, using CR equations. Based on the above results, maintain the following results are valid. That is, first one, dou by dou x of modulus of x modulus of f of z whole square plus dou by dou y of modulus of f of z whole square is also equal to modulus of f dash of z whole square. If psi is any differentiable function of x and y, then dou psi by dou x whole square plus dou psi by dou y whole square equal to dou psi by dou u whole square plus dou psi by dou v whole square, that is also equal to modulus of f of dash of z whole square. Next one, dou square by dou x square plus dou square by dou y square into real of modulus of f of z whole square equal to 2 into modulus of f dash of z whole square, and then dou square by dou x square plus dou square by dou y square into modulus of f of z whole square equal to 4 into modulus of f dash of z whole square. Next, construction of an analytic function when real or imaginary part is given. Suppose the real parts or imaginary parts are given. The Cauchy-Riemann equations provide the method of constructing an analytic function f of z equal to u plus iv when u or v or u plus iv u plus v is given. Suppose u is given, We determine the differential dv, hence v equal to v of x comma y, dv equal to dou v by dou x into dx plus dou v by dou y into dy. Using CR equations, this becomes dv equal to dou u by dou y into dx plus dou u by dou x into dy, that is equal to mdx plus ndy. And it is clear that dou n by dou x minus dou m by dou y equal to dou square u by dou x square plus dou square u by dou y square equal to 0. Because u is harmonics, this shows that m dx plus n dy is an exact differentiable. Consequently, v can be obtained by integrating m with respect to x by treating y as a constant and integrating with respect to y only those terms in n that do not contain x and adding the result. Similarly, v is given by using du equal to dou u by dou x into dx plus dou u by dou y into dy, that is also equal to dou v by dou y into dx minus dou v by dou x into dy. Following the procedure explained above, we find u and hence f of z equal to u plus iv can be obtained. Next one method, Mill-Thomson method. An alternative method of finding u plus iv when u or v or u plus v is given. Suppose we are required to find an analytic function f of z equal to u plus iv when u is given. We recall that f dash of z equal to dou u by dou x minus I into dou u by dou y. Let us set dou u by dou x equal to phi 1 of x comma y, dou u by dou y equal to phi 2 of x comma y. Then f dash of z equal to dou phi 1 of x comma y minus I into phi 2 of x comma y. Replacing x by z and y by 0, this becomes f dash of z equal to phi 1 of z comma 0 minus I into phi 2 of z comma 0, from which the required analytic function f of z can be got. Similarly, if v is given, we can find analytic function f of z by starting with f dash of z equal to dou v by dou y plus I into dou v by dou x when u plus v is given. Next, applications of flow problems. As the real and imaginary part of an analytic functions are the solutions of the Laplacian equation in two variables. The conjugate functions provide solutions to a number of field and flow problems. Let V be the velocity of two-dimensional incompressible fluid with irradical motion. V equal to dou V by dou x plus I into I plus dou V by dou y into J. Since the motion is irrotational, curl V is also equal to 0. Hence, V can be written as del phi equal to dou phi by dou x into I plus dou phi by dou y into J. Therefore, phi is velocity component, which is called the velocity potential. From 1 and 2, we have dou V by dou x equal to dou phi by dou x, dou V by dou y equal to dou phi by dou y. Since the fluid is incompressible, di V is also equal to 0. That is dou by dou x of dou phi by dou x plus dou by dou y of dou phi by dou y equal to 0. This indicates that phi is harmonic. The function phi of x comma y is called a velocity potential, and the curves phi of x comma y equal to c are known as equipotential lines. Note that the existence of conjugate harmonic function psi of x comma y, so that w of z equal to phi of x comma y plus I into psi of x comma y is analytic. The slope of the given equation by dy by dx is also equal to dou psi by dou x divided by dou phi by dou y, that is also equal to minus dou phi by dou y divided by dou psi by dou x, that is vy by vx. This shows that the velocity of the fluid particle is along the tangent to the curve psi of x comma y equal to c. The particle moves along the curve. Psi of x comma y equal to c is called the streamlines. Psi of x comma y phi of x comma y equal to c is called the equipotential lines. As the equipotential lines and the streamlines cut orthogonally, therefore dw by dz equal to dou phi by dou x plus I into dou psi by dou x, that is also equal to dou phi by dou x minus I into dou phi by dou y. The magnitude of the velocity equal to root of Vx square plus Vy square equal to, that is modulus of dW by dz. The flow pattern is represented by the function W of z known as complex potential. The complex potential W of z can be taken to represent other two-dimensional problems, that is steady flow. In electrostatistics, phi of x comma y equal to c interpreted as a equipotential lines, psi of x comma y equal to c1 interpreted as lines of force. In heat flow equation, phi of x comma y equal to c is interpreted as isothermal lines, psi of x comma y equal to c1 interpreted as a heat flow lines. Cauchy-Riemann equation in polar form. Let f of z equal to u of r comma theta plus iv of r comma theta be analytic, then there exist four continuous first order partial derivatives. U r equal to 1 by r into v theta, v r equal to minus 1 by r into u theta. Next one, harmonic function. The function phi is said to be harmonic function if it satisfies the Laplace equation del square phi equal to 0. Let f of z equal to u of r comma theta plus iv of r comma theta be analytic. We shall show that u and v are satisfy the Laplace equation in polar form. There is dou square phi by dou r square plus 1 by r into dou phi by dou r plus 1 by r square into dou square phi by dou theta square equal to 0. The CR equation in polar form are given by u r equal to 1 by r into v theta, v r equal to 1 by r into minus 1 by r into u theta. Differentiating 1 with respect to r and 2 with respect to theta, partially we get r square into dou square u by dou r square plus dou u by dou r equal to minus 1 by r into dou square u by dou theta square. Dividing by r, we get dou square u by dou r square plus 1 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square equal to 0. Hence u satisfies Laplace equation in polar form. The function is harmonic. Similarly, v is harmonic. Next one, orthogonal system. What is orthogonal system? Let r equal to f of theta and tan phi equal to r into d theta by dr, phi being an angle between the radius vector and tangent. The angle between the tangent at the point of intersection of the curves is phi 1 minus phi 2. Then tan phi 1 into tan phi 2 equal to minus 1 is condition for orthogonal. Thank you.